Hello and welcome back to Calculus 1, section 4.7 on L'Hopital's rule. We are going, well, it's Bernoulli's rule, but it's fine. Look up the history. So L'Hopital's rule, we are going to take a look at how to take the limit, amongst other things, as x goes to 0 of sine x over x, right? You know the methods from chapter 2. Plug in. That's the first method, and if that works, you're done. Well, unfortunately, if you plug in now, you get sine of 0, which is 0. You get 0 over 0. Yeah, that doesn't do well, right? And then you wonder, you know, why and how, because you were told to memorize, why and how is this 1? So L'Hopital's rule is the rule that addresses these types of questions. So anytime, and here's, we're going to do this in blood, anytime we have 0 over 0 or infinity over infinity, we use the following rule. Limit as x goes to a of f of x over g of x by L'Hopital's rule will have the same value as limit x goes to a of f prime of x divided by g prime of x. Please read this formula very carefully. Over here, these are individual derivatives. Not quotient rule. So, your function f of x on top is completely detached from g of x in denominator, and you are taking independent derivatives. Note that in notation I did not put derivative of this. Derivative of that will be quotient, right? We are taking independent derivative on numerator from denominator, and each one is a separate calculation. What rule shows is that answer for the limit on the left, which we can't compute because we get 0 divided by 0, is the same as the limit that we might be able to compute on the right. You are allowed to use this method over and over and over and chain it as many times until you run out of 0 over 0 or infinity over infinity prerequisite, right? So, the sentence above this says, if you have 0 over 0, like we have sine x over x, that's 0 over 0. If you have that, you are allowed to take independent derivatives and then see what happens. If you don't have that, then whatever other derivatives, whatever other technique you can do. So the first problem that we are going to test this on is our good old limit of sine x over x, because I know that you lost countless hours of sleep over not knowing how's this one. Well, we have 0 over 0. I generally put different color to indicate that I plugged in 0 and it worked out to be 0 over 0. That allows me to use L'Hopital's rule, so you would put this L apostrophe H above equal sign. And then limit x goes to 0. The derivative of sine x is cosine x, and derivative of x is 1. you cannot just put equal sign. You must put this L apostrophe H, because these two are not equal. They are not equal, right? They're not equal. However, the result from taking the limits of the function is equal, right? So now we have cosine of 0 over 1, which is 1 over 1, which is 1. And lecture is over, right? This is L'Hopital's rule. I'll give you also an example for infinity. Now, what is actually the issue with the lecture? There are many other forms that you can transform into this. When you have multiplication of the two, 0 times infinity, infinity minus infinity, 1 raised to infinity, 0 raised to infinity, 0 raised to 0. All of these forms can be eventually transformed into this. So that's where the chunk of our lecture is, to go through all of the cases that eventually result in L'Hopital's rule. But we are done with learning L'Hopital's rule with this, because that's all it is. If you have 0 over 0 or infinity over infinity, take independent derivatives and plug the value again. If you get 0 over 0 or infinity over infinity again, take again derivatives and keep taking that until you reach the point where when you plug numbers in, you don't get 0 over 0. Well, then, as you can see, over here I don't have 0 over 0 anymore. But when I plug values in, I get cosine of 0, which is 1. I get 1 over 1. Well, that's 1. And there we go. Problem solved. Infinity over infinity. Remember the long and painful procedure of dividing by the highest exponent to find the horizontal asymptote, right? That was a few steps of algebra and a lot of canceling. What is the horizontal asymptote? So you have x goes to infinity for, let's say, x cubed minus 3x plus 1 divided by, I don't know. How about, there's too many threes. I can't think of other number, 4. Thank you. Cubed, and I heard 8, so here it is. Plus 8x squared minus 7, because it's annoying. So when you plug in your infinities now, you will have infinity over infinity, right? This is infinity over infinity. Infinity cubed minus 3 times infinity, that's all infinity, plus 1 over there. And then you have the infinities on the bottom, minus 7, right? This is infinity over infinity. So now, L'Hopital's rule, limit, x goes to infinity, and what do? Take derivatives. 3x squared minus 3 divided by 12x squared plus 16x. Plug infinity, what do I get? Infinity over infinity again. So, L'Hopital again. L'Hopital, we get, make sure you're copying this limit every line. What do I get? Another infinity, another derivative. I get 6x divided by 24x plus 16. Plug in infinity, what do we get? Infinity over infinity, right? So pick your poison. Do you want to do this or do you want to do canceling? Limit x goes to infinity. Again, L'Hopital's rule. So taking derivatives. 6 over 24. Well, that's a quarter. We knew it was a quarter already because it's the same exponents and just front coefficients. But, you know, at some point we have to show off the L'Hopital's rule for infinity. So these are, you know, the basic, or as you would say, vanilla uses for L'Hopital's rule. two examples, one 0 over 0, the other one infinity over infinity. And those are the only two cases. The rest that I'm going to talk about now are all, we have to use some kind of algebraic witchcraft or whatever to transform it into this form to do L'Hopital's rule. So the first case that we are going to consider is going to be 0 times infinity. So 0 times infinity case. There is a very nice trick, algebraic trick, that we are going to use to transform this into forms we need. You have to figure out how to get 0 over 0 and infinity over infinity, otherwise this all fails. So the coolest thing ever, over here, in my humble opinion, is that f of x can be written as 1 over f of x. This is just algebraic truth. What happens, if you want to prove this, what happens when you multiply top and bottom by f? The bottom will cancel, the top will survive, and there you go, f equals f. Great. So this works. You must memorize this. And when you run into a case 0 times infinity, you will do this. I have one of my previous students from 2-3 years ago who is doing computer science at one of the universities and messaged me with how do you take this limit. It's a computer science higher end course, 400 level computer science course, and the homework was, as he described it, a little bit too much math and not much computer science. So, yeah, that was something that we're doing. And he had the question on a particular problem. And I said back in a message, well, it's the limit with L'Hopital's rule. And I should have taken a screenshot of that. And he's a gamer as well. So he says, with exclamation like, L'Hopital, I forgot about that. Well, I'm thinking, yeah, it's been 3 years. And then maybe 30 minutes later, it says, L'Hopital is coming in a clutch because it solved all of the homework problems, all 5 problems on that problem set for homework were actually L'Hopital's rule. So yeah, this stuff is going to show up, so pay attention right later on. So we have f of x equals 1 over f of x. Let's pick immediately an example. Oh, this is wonderful. Limit x goes to infinity of x squared times sine of 1 over 4x squared. It's beautiful. So what happens as I plug in x equals infinity? Well, infinity squared goes to infinity times, and then what's 1 over infinity? 0. Sine of 0 is 0. So this fits our 0 times infinity case, right? So what I'm going to do now is I'm going to take this x squared and using the formula 1 over f, write x squared as 1 over x squared. So I'm not doing L'Hopital's rule here. I'm doing basic algebra manipulation. So this becomes sine 1 over 4x squared divided by 1 over x squared. This is algebraic manipulation. Now I check again. Plug in infinity. 1 over infinity is 0. Sine of 0 is 0 on top in the numerator. And then 1 over infinity squared is 0 in the denominator. Aha! So using this algebraic manipulation, we were able to transform our problem that is infinity times 0 to 0 divided by 0. In some cases, it would be infinity divided by infinity. We don't care, right? We just got what we need, and now unleash L'Hopital. So we have to take independent derivatives. How are your derivatives now? All right. So what do we have? At least it's not a quotient rule, right? So we can enjoy separate. What's a sine, derivative of sine? Very good. And we copy the guts, right? So 1 over 4x squared. And then times, in the chain rule, the derivative of the inside, right? Which is times negative 8? No. Exactly. You see what happens? So we just go on a side. We have to deal with 1 quarter times x to the minus 2. We're not going to crank quotient rule for that. Yes. So we have copy the constant, and we have negative 2 x to the negative 3. So negative 1/2 x cubed on the bottom. Are we agreeing on this? Great. And now, if you are taking only the derivative of x negative 2, oops, I'm supposed to put these derivatives for complete notation. I have negative 2x to the negative 3, so that's negative 2 over x cubed. So that's negative 2 over x cubed. These x cubes will drop. And now we just deal with the rest of the algebra. So limit x goes to infinity of now this 2 and this 2 and the negatives cancel as well. So this becomes 1/4 cosine of 1 over 4x squared. Now when you plug in infinity, you get 1/4 cosine 0, which is 1/4. Who would say when you multiply 0 times infinity, you get a quarter, right? How cool is that? Wait for us to subtract infinity minus infinity and get like 1/3. That's going to be awesome too. It's coming up. Give me 15 minutes. So, we used algebraic manipulation to convert 0 times infinity into 0 over 0. And then we did L'Hopital's rule, independent derivatives, top and bottom. And then more algebra to cancel x cubes and negatives and shovel these things around. And at the end, we have cosine of 0 is 1. Answer is 1/4. Let's do one more of these problems and then move to the next case, infinity minus infinity. But let's do one more of these. Now, on the exam, does it say solve infinity minus infinity case? No, it just says take the limit. Just like that homework in computer science, right? Take the limit. That's it. So good luck. I have to jump into homework, which is like about 15 pages away. There we go. You like trig, right? That was the... So, problem 57 from the new textbook. No, 53. Says limit x goes to 0 of x cosecant x is equal to what? There you go. Have fun. Are we done? It's one step. Limit x goes to 0. The cosecant is 1 over sine, so this is x over sine x, and it's equal to 1 eventually. I know. So this is 1 over cosine, which is the same as cosine over 1, whatever. Yeah. So in red, 0 over 0, which is equal to limit x goes to 0, 1 over cosine x, which is 1 over 1, which is 1, and infinity minus infinity case. Cool, huh? Of course, cool, it's math. Let's go. Good. That was a good one. So now, for infinity minus infinity case, we have to think a little bit. Hopefully we agree that 0 over 0 and infinity over infinity both are within division, right? 0 divided by 0, infinity divided by infinity, that's division. You have subtraction. So how do you go from subtraction to a division? Nope. Nope. You go through factoring, because factoring is going to make it multiplication, and then you will hopefully have 0 times infinity, use the trick 1 over f, 1 over 1 over f, to get to where you need to go. So these are the problems. Remember how I said warm up? So that's this now. All right, new page in the notebook, so you can fit the problem and actually see it in full when you limit x goes to infinity of x minus square root of x squared minus 3x. Is this infinity over infinity? I mean, infinity minus infinity? Sure. Right? When x goes to infinity, and then under the square root of infinity is infinity. So this is definitely infinity minus infinity. Great. Now remember what I said. The way to go from infinity, minus infinity, all the way to any of the two forms we need is through factoring. Because you first have to create multiplication, and then that multiplication will become division when we use the previous trick. Well, what do I get to factor? Well, I better have some x over here that I can factor with this x over here outside so that I can do all of this. So now I need this x. Well, that x has to come from here, so I need to fix that. So it's a ripple effect, right? When you have what you want and what you have, and then you go through steps. So limit x goes to infinity, x minus, and over here I am factoring x squared, which gives me 1 minus 3 over x. I understand that there's no x squared here, but you can force it. It's okay. So now this x squared can go in front as x, because square root of x squared is just x. So now we have x minus x, square root of 1 minus 3 over x. And here is where the factoring happens. Limit, oops, this is infinity. X goes to infinity. Factor out x, we got 1 minus the square root of 1 minus 3 over x. Now you wonder, what is this? Right? Because you factored, now you have multiplication. What do you need in order for the problem to work? You need 0 times infinity, right? Because then you can use the trick. So is this 0 times infinity? Well, of course it is. Because when you plug in infinity here, you have your infinity times. Plug infinity here, what do you get? 0. 1 minus 0 is? 1 minus 0 is? 1. Square root of 1 is? 1. And 1 minus 1 is? 0. There we go. So the whole thing over here is 0. Excellent. Now that just means that now we can use 1 over f. So this x gets kicked into denominator. 1 minus square root of 1 minus 3 over x stays in the numerator, and then you get 1 over x in denominator. By the way, if you are confused by all of this stuff, this is your main division line, and this number 1 gets multiplied into the numerator, like whatever is staying. So you never see this 1 on top. You only see what's under the main division line. That's a little bit of algebra there, so go and figure it out. What do I have now? Well, we know that top is 0 already because it's the same as before. What's the bottom? Bottom is 1 over infinity. What's 1 divided by infinity? Another potato. Very good. So now we have 0 over 0, and that is L'Hopital. So now we take the limits. Take the independent derivatives. Well, let's deal with the denominator first, because that's cheap. By the way, you might want to memorize this derivative, just like a square root. Right? 1 over x is negative 1 over x squared, because it's going to show up so many times that you'll be sick of it. If you have to go every time, x to the minus 1 is, minus 1, x to the minus 2, and then fix it. Just, What do I have on top? Derivative of 1 is 0. Then I have negative 1/2 of 1 minus 3 over x to the negative 1/2. That's the derivative. Times the derivative of the inside. And on the inside I have derivative of 1 is 0. Derivative of, so 3 over x squared. right? Because there is a negative here, and then there's negative that pops up from the formula. So it's positive 3 over x squared. So these x squareds are going to drop. And when I plug in infinity, the entire parenthesis becomes 1. So 3/2. Let me do another step. So what's left? Limit x goes to infinity. And I have, so negatives will cancel. I have 3/2 times 1 over square root of 1 minus 3 over x. That's the only thing that is left, which is 3/2, because the square root is 1, right? 3 over infinity is 0. 3 over infinity is 0. 1 minus 0 is 1. Square root of 1 is 1. 1 divided by 1 is 1. So the whole thing is 1, and the only thing is left is 3/2. So what's infinity minus infinity? In this case, I can actually make it to be anything I want just by playing with numbers. Now go ahead, change this 3 into a 5, and see what happens as it propagates through the calculation. Right? You all know what's going to happen. The 3 in the answer becomes 5 in the answer, right? So you can, and then you can put the fractions there, and you can literally make infinity minus infinity to be any number you want through this particular problem. Just use carefully, you know, which fraction or which whole number you're going to put instead of that 3 there. And then when someone says, what do you know? How about infinity minus infinity is 4.5? What? Yeah, welcome to Calculus1. Yes. So, this algebraic witchcraft over here. Okay, let's take a look. Don't worry about it. I'm a professional. So in order to have x over here, I have to have x squared that will generate that x when it gets out of square root, right? But I need this x squared. Well, I can get x squared easy from the first one. The second one, I just multiply x over x. So I have x squared on top. So x squared common, but then I gain the one on the bottom. So now this x now goes outside, and then this x and this x comes up here, and then I have 1 minus 1, but I don't write the 1 in front of the root, right? And it goes that way. And yeah, so I can't make it better, I can just make it worse. But there's that part. Once you are at the point with infinity times 0, that's the previous case we just learned, use the trick, right? And there's the L'Hopital. Good luck with the derivative, obviously. Just please make sure that you are doing independent derivatives, right? Clearly, quotient rule would make this even worse, right? So, you know, 2 simpler derivatives would be better than the 1 quotient rule over there. So, it's independent derivatives, and that's all it is. So, yes. I can't hear you.
Can you explain how 3x is 1 minus 3 over x?
How 3x is 1?
I think how you factor it out.
You are talking about this.
Yeah.
Well, that's what he asked. I said x squared minus, and then I'm just going to do 3x squared over x. I multiply by x over x on the second term. So now when I do that, I have a x squared on top. So x squared, when I factor 1, right, from here, minus x squared is gone, so it's just 3 over x is left. And that feeds into the next line, and then x squared escapes the root, and then the rest is history of 20 minutes of calculating. Good, huh? Love it. Let me ask you a quick question. What's 1 times 1? Times 1? Times 1? Times 1? Times 1? Times 1 times 1 times 1 times 1 times 1? Times 1 times 1 times 1 times 1? So what's 1 to infinity? Yeah, not 1. This is, it reminds me always as a kid, when they ask you, how fast can you say the word milk?
Oh.
How fast can you say the word milk? Milk, milk, milk. How fast can you say it? Do we have someone who would like to try that?
Yeah.
No.
How fast can you say milk?
You want to do like a trial for like 10 seconds? And then multiply and see.
Shoot, yeah, okay, fine. 10 seconds is, how you do 6 seconds?
6 seconds? Okay. It's more like
Okay. Go.
Milk, 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 milk.
What does cow drink? All right. Packs his stuff, leaves the lecture. Okay. All right. Every time I do this, I remember that one. I can just make it worse now. I fell for that in 6th grade. All right. So, yeah, I don't know. Anyway, so it works pretty much all the time. That's nice. So what do we have now? We have these cases of 1 to infinity, 0 to 0, and infinity to 0, and they're all solved the same way. So the first case we already talked about. 1 times 1 times 1 times 1 times 1 is 1, right? But if you have infinitely many 1s, somehow they work out to be not 1. And we're going to do that calculus, actually. And now, what is 0 raised to 0? 0 raised to anything is 0. And anything raised to 0 is 1. So 0 raised to 0, which is it? Is it 0 or is it 1, right? You see the dilemma there. And then finally, infinity raised to anything is infinity, and anything raised to... You see? So, welcome to calculus, right? Because in algebra, they tell you that anything times 0 is 0, and we just did 0 times infinity and got like a quarter, right? So see, already we negated that algebra thing. And in algebra, they also say 1 to the n equals 1. Well, apparently, we're going to just break that now as well. So what is the proper technique to deal with these things? Well, let's take a look at the limit as x goes to infinity of 1 plus 1 over x raised to the x. Do we all agree that this is 1 to infinity case? I hope we do, because if x is infinity, 1 over x is 0, so inside parentheses you have 1, and then exponent x goes to infinity, so it's 1 to infinity. So this is that case. Now, the method that I'm going to use for this particular problem works for all three. right? It's just the matter of you recognizing that you have one of these three cases, and then you will unleash the method that I'm about to show. So we start from setting the whole limit equal to y. I need to get rid of this exponent. You see what's coming, right? How do I kill the exponent? Log, very good. Now that leads into the product, and it's going to be beautiful, epic, as you would say. Y equal, yeah, I know, limit of 1 plus 1 over x raised to the x, and this is where we go and say ln both sides. Ha. Now, ln and limit can swap. ln is the increasing function. You take advanced calculus, you will have to write a page proof in between. Right now, you know, I said so. You can swap limit and ln. One is a function, the other one is operator. So there's some work to be done there, but that's okay. So now we have ln y is equal to the limit x goes to infinity. Oops, I missed x goes to infinity here. And we know that when you have this ln of 1 plus 1 over x, the exponent x will jump in front. I'll write the formula from before. You should know it, but again, ln x to the p is p ln x. So that's how this exponent x ended up in front of ln. Shall we test this? What is the x times ln? So x, that's infinity. Okay, let me put nice infinity over here. And what is 1 over infinity? 0. And what's ln of 1 now? Yeah, there we go. Woohoo! So we transformed our 1 to infinity into infinity times 0. So we use our regular witchcraft 1 over f, right? Push that x in the denominator. So please note that on the left-hand side, you still have your ln y. You will have to deal with that, right? We are just working now our right-hand side. This is still limit. We didn't do anything with it. I have my ln of 1 plus 1 over x divided by 1 over x. And yay. This is infinity over infinity, which means we can use L'Hopital's rule. So now ln y equals, and here is the L'Hopital limit x. And now we take the derivative. Well, the bottom is immediately, right? You memorized this one by now, I hope. Right? Derivative of 1 over x is negative 1 over x squared. I told you you're going to see this 17,000 times just in this lecture. So you might as well memorize the derivative of 1 over x. The top. Well, we know what the ln derivatives are. You take the argument, write it in denominator, and put its derivative on top. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. Now this is the part where I should just take a screenshot and bring it to my intermediate algebra class, because the question arises when they do complex fractions, when we are ever going to use this in real life. Well, obviously the answer is nowhere, because you're still in your fake life in college over here. So here you go. Yeah, this is what was on the test today for them. The fastest way to deal with this, obviously, if I should use that word, is to first kill off these negative signs and then multiply x squared to completely kill the denominator of the big line, right? 1 over x squared gets completely annihilated by x squared. So there's just the upper fraction to deal with. So ln y is equal to the limit x goes to infinity. And now this line here becomes the main division line. The denominator is all gone and canceled. I have 1 plus 1 over x in the denominator, and then the numerator is just 1. Because, so this x squared kills this x squared, and this x squared kills that x squared, and that's it. Well, this is great. I got 1 over here, right? 1 over infinity is 0. So I have 1 over 1, which is 1. Don't forget this. You are not done. What you have is ln y is equal to 1, which means y is e. You e both sides to kill ln. So y equals e to the 1, which is e. Now, what was y? Y was the entire problem, right? Do we remember that? That y was the entire problem? So, the limit of 1 plus 1 over x raised to x as x goes to infinity is equal to e. Yeah. You remember the definition for e? As your proof. Should we flip through the book back to the 3.8, I believe, when I gave the definition for e, and then we did derivatives and derivatives of exponentials and logarithmic. I think it was 3.8, and then logarithmic differentiation, right? That was previous exam. There's the proof for, and what did we just found out? We found out that 1 to infinity is equal to e. Fine. Right? All right, great. So there's your definition for e. And this was the case 1 to infinity. So now you go and you figure out other wonderful cases that you might experience. So let's go and see what else they have. And then we still have to talk about something else. This is something, let's see something quick. Oh, beautiful. This is, you're going to love this problem. What is the, this is 78. What is the limit as x goes to 0 plus of sine x raised to the tangent x? Now, I understand that half of you are probably going, but why? And I'm on that boat as well. The answer is because we can. I don't know any application for this, but since we can exercise mathematical gymnastics, why not? Y equals this. ln both sides drops the tangent in front, 0 times infinity, work it out, right? And after a page of calculations, there you go. You get like 7, I don't know. Let's see what we get. So y is equal to limits of sine x raised to the tangent x. We ln both sides. That will drop. So now limit goes in front, x goes to 0 plus. Tangent x goes in front. Ln of no coughing sine x is here. And now when I do the derivative, when I check, tangent of 0 is 0, and sine of 0 is 0, ln of 0 is negative infinity. So I'm going to draw this graph over here if you have issues with ln. So this graph is your ln x graph, and do we all see that as x goes to 0 on this graph, the value shoots to negative infinity? Now, negative infinity and positive infinity in the projection onto the 2D graph is actually the same point. So there's no difference between positive infinity and negative infinity in general. So this whole thing is going to work just fine. So we just put tangent in denominator, and from here on there's going to be a lot of trig identities. Good thing that we reviewed that trig identity with n and a 6 earlier. It's going to help here. So what do I have? I have ln of sine x divided by, and now this is 1 over tangent. So do we all agree that that's a cotangent x? So tangent x is equal to 1 over tangent, but 1 over tangent x is just cotangent x. So just write it for what it is. So now, when you check, it becomes infinity over infinity. I mean, negative infinity, and the cotangent graph is like this, so becomes infinity here. So now I have ln y, and I use the L'Hopital's rule now. Numerator, put sine x, the derivative of sine is cosine x, that goes on top, and derivative of cotangent is very good. So that's limit x goes to 0 plus. What is the cosecant squared? All right, good. So that's cosine x over sine x, negative 1 over sine squared x. No, you're right. Which is, oh, should I put ln y? I don't want this to be lost. Is limit x goes to 0 plus of, and then I have negative sine squared x cosine x divided by sine x. So one of the signs will drop, and finally I have that the ln y is equal to the limit x goes to 0 plus, and now I have negative sine x cosine x, which is equal to 0. So ln y is equal to 0, e both sides, y equals to e to the 0, which is 1, and finally limit as x goes to 0 plus of sine x raised to the tangent x is equal to 1. This is excellent conversation starter for your Thanksgiving dinner. So I am promising you no one will be bothering you next year. So pull this one out, put it on a table. Especially if you work it out with a pen on one of those fancy, you know, linen tablecloths. Yeah, exactly. Yeah.
No, that's funny. I just went out to dinner last night with my friend. I haven't seen her in like forever, and she was like asking me like what I was in school. I told her I was in calculus right away. She was like, top. Here.
See, if it was just one night later, like tonight, you would have so much material. Like after this, did you know actually that 0 times infinity can be? It's amazing, right? I just need a few more seconds to talk about the fast way of figuring out limits when you have functions that are not compatible. I mean, yeah, for algebraic manipulations and so on. What happens if you combine exponential with a polynomial or logarithmic with a square root or something along those lines? There is this wonderful, this is the end of the lecture. So the last 2 pages have this, and this will be expanded on in Calculus 2 when you do sequences and series. They will add factorials and some other things. We're talking about growth rate of functions for 2 minutes, and that's it. Growth rate of functions. So certain functions grow faster than others. You know that the even figure of speech would say grows exponentially, right? And you ask them to write exponential function. They don't know, but they know it's just that, you know, in math, that is a function that grows fast. There are much faster functions than exponential function, but that's, right, reserved for you, cognitive elite over here. So what are we going to do? We're going to start by saying that ln raised to some power q of x is the slowest of all functions. That one is sluggish. And that is going to be followed by, this is a double less than sign. Okay, so that's the notation. Polynomial functions. We are talking about square root of x. We are talking about x to the x squared, x to the 100th power. That is smaller than when you multiply these two together, and that should be common sense. So x to the p ln to the qx. All of that is smaller than when you multiply 2 polynomials, because their exponents would add, which is further smaller than, here is your exponential function, and now what I call the boss function at the end over here, x to the x. It is very simple to see how these values grow if you just have x, 2x for linear function, x squared, 2 to the x, and then x to the x. And you just run few values. 1, 2, 3, 4, 5. Right? If you do first 5 values, immediately it will be clear that as you move this way, functions grow faster. So 2, 1, 2, 1. Actually, let me go one by one. So 4, 6, 8, 10. This is when you have 2x. The growth goes 2, 4, 6, 8, 10. For x squared, you have 4, they're tie, and then here 1 with 9, and then 16, 25. So clearly x squared grows much faster than the 2x. Now 2 to the x gets you 2, 4, 8, still losing, right? But now 16, and then 32. So it took some time for exponential to catch up to x squared, but once it did, it's going to take off, and x squared will have no chance ever in catching up. Exponential function. But look what happens with x to the x. It's 2 to the 2, that's 4. 3 cubed is 27. 4 to the 4. 4 to the 4 is what? 16 squared is 256, right? 256. Look at that. Like 5 to the 5, I'm just going to put a lot, all right? and then you can go from there. So x to the x is, now why is this really cool for limits? Like, why is this really cool for limits? Because in quotation mark, this is not official mathematical notation. This is me just talking over here. Limit as x goes to infinity of slow over fast, because they're all on this scale somewhere, right, in that long line up there. Slow or fast is going to be 0 all the time. And limit x goes to, this is only for infinities, fast over slow is going to be infinity, exactly. This is what it is. So you can use growth rate of functions if you have a polynomial matched with exponential, polynomial on top, exponential on the bottom, it's 0. If you flip them, it's infinity. Cool? See you next week.